All right, let's get started. We're a couple minutes past the hour. Seems like we're hitting critical mass right now. Welcome everyone to the 41st ECS and Cloud Feedback Virtual Symposium. Thanks for joining on this Friday morning. Today we're going to have three speakers. It's going to be a broadly kernel-themed month. So we're going to have Janoski from NOAA-CESSRST, Mark Zelinka, and Brandon Duran, and I think we'll be having them speak in that order. This is going to be three short talks, about 12 minutes, with questions after each, and then the short general question and answer after the last talk. This is just our normal format. Please type questions or comments into the chat at any time. And then if you'd prefer at the end to ask questions, you can raise your hand and we'll unmute you. If you are interested in giving a talk in the future, please reach out to myself, Sha Lee, Nick Lutzko, or Andrew Williams. And if you want to see videos of past talks, mailing list signups, committees, whatever, please visit our website. And the last thing I'll say is thanks so much for everyone joining. Obviously, yesterday was a pretty difficult day in the US for climate science with NOAA layoffs. Makes me think that this symposium first started in order to kind of build community during the pandemic about 5 years ago. So hopefully we can continue to keep building that community and keeping it strong. So let's start with Tyler to start off.
Everyone see
Looks
that?
good.
Okay. Nice. All right. My name is Tyler Janoski. I am a postdoc at NOAA-NSSL and City College of New York. And I'm going to be talking about ClimKern, which is our Python package and kernel repository for calculating radiative feedbacks. Because this is a kernel-themed seminar today, I figure we'll do just some brief review. Consider a climate system where we impose a radiative forcing, say, from an increase in CO2. Our total radiative imbalance at the top of the atmosphere will be the sum of the radiative forcing and the net climate feedback parameter multiplied by the global mean surface temperature response. It's common to linearly decompose the net climate feedback parameter into individual feedbacks, so temperature feedbacks, water vapor feedbacks, surface albedo feedbacks. The feedback from a change in some field, again, temperature could be specific humidity, is equal to the partial derivative of the top of atmosphere radiative flux with respect to that variable times the change in that variable. And when we say radiative kernel, we're referring to that partial derivative term. What makes the radiative kernel method so popular is that you're able to use existing or pre-calculated radiative kernels to diagnose feedbacks. This eliminates the need for the labor-intensive process of generating your own kernels, which, if you're using a climate model, can involve running offline radiative transfer code at short time steps. In our experience, we've found at least 15 sets, probably more like 20 sets of radiative kernels created from a mixture of models, reanalyses, satellite observations. And there's this underlying assumption that the interkernel variability is much less than the differences in the climate responses between models. What this means is that kernels do not have to be derived from the same model or data type in which you're calculating radiative feedbacks. So if you can use radiative kernels from model X to diagnose radiative feedbacks in model Y. However, there are some challenges that come with using radiative kernels. There's no standardized way for these calculating these feedbacks. These computations require making assumptions. How do you vertically integrate from the surface to the tropopause? What is the base state temperature and humidity that you're using? And that makes it so that even if you have the same model output and kernels as someone else, you can still perform these calculations using a physically reasonable approach and get different values than the original calculations. There's also no central repository for radiative kernels. They're often scattered among different research groups, and you have to go hunting to try to find them. And even when you find them, they have different data structures, units, and sign conventions. This means that normally grad students waste hours deriving the same calculations that other grad students and scientists have done before, and it's super inefficient. Lastly, we question that assumption whether interkernel variability is really negligible compared to intermodel variability. The end result of this is that there's decreased reproducibility in climate feedback studies. To address this, we made the ClimKern Python package and data repository. Starting with the data repository, we found 11 sets of kernels that met certain criteria. We required them to have a top of atmosphere air temperature, surface temperature, water vapor, and surface albedo kernels. They also needed to have clear sky and all sky versions, so without and with clouds. After acquiring these kernels, which are listed in the table on the right, we standardized the nomenclature, the signs and units, and made sure that they were all on pressure levels so that they were compatible with both each other and whatever data the user may input into the Python package. Lastly, we did a little quality control. An example of this is the ECM5 kernels have been used in several past studies. At least in the form that we've been able to acquire them, there are some obvious issues with them. So those were removed from our original set of kernels so that someone who's accessing our repository can at least be confident that they will get physically reasonable feedback values using our these specific set of 11 kernels. The Python package was made to make calculating feedbacks way easier than coding yourself. The install is simple. It's available on the Python package index. It's just pip install ClimKern. There's a function to automatically download the entire ClimKern repository to your machine so that the kernels are stored locally. There's functions for temperature, water vapor, surface albedo, and cloud feedbacks, both the adjustment and residual methods for the latter. And it's compatible with most GCM and reanalysis output. It's definitely compatible with CMIP output. It can intelligently parse units and data structures and also alert the user if it detects either kind of wonky units or whether something might be incorrect. And we included plenty of options. You can specify the kernel that you use, how you want to define the tropopause, whether you're calculating all sky or clear sky. There's functions to calculate them using the fixed relative humidity method, and several variations of water vapor feedback calculations. I have a snippet here of what it might look like in practice. You import the package like you would with import ClimKern. In this case, we load in some sample or tutorial data that I'll talk about in a bit. And to calculate the temperature feedbacks, there's just a calc-t feedbacks function. It produces the lapse rate and Planck feedback, and it requires the control simulation and the user perturbed simulation temperature, surface temperature, pressure, and some of these optional parameters. There's a quick start guide on the GitHub that I'll show later that even includes values for the user to test to make sure everything's working okay. As an example of one of these complications that ClimKern tries to simplify is the water vapor feedback calculation. So from experience in coding this ourselves, water vapor kernels typically are in the form of per unit temperature. That requires a normalization by a factor that's the specific humidity increase per unit warming so that you can get your water vapor kernel per unit specific humidity. Now, ideally, this would be done using the simulation that actually produced the water vapor kernel that you're using. Unfortunately, this is rarely included in any kernel sets that I've seen. So what ClimKern does is it calculates it from whatever control simulation the user is providing to calculate the feedbacks. There's some choices that go into it too. Past studies have used either the linear or logarithm of the specific humidity response. And if they use the logarithmic change, we've found studies and other people's code that where they use a fractional approximation for logarithms, basically that the change in the natural log of specific humidity is approximately the linear change normalized by the control specific humidity. ClimKern offers 4 different methods, which are outlined in the documentation based on these choices, so that the user can specify exactly which way they want to do it and even compare results between methods. I'm now going to show some results using just a single model. In our sample data, this is included in the ClimKern repository. It's just 2 single simulations with the large ensemble configuration of CSM1, a pre-industrial control, and an abrupt 2 times CO2 simulation. And for the cloud feedbacks, you need the radiative forcing. We use the effective radiative forcing that we calculated from fixed sea surface temperature simulations. Here, I show the annual mean vertically integrated feedbacks in our sample CSM data. And on the left, that is the kernel mean feedback values. And on the right, so the plots in the purple, are the kernel standard deviation feedback values. As you can see, the lapse rate and Planck, and really all of them except for the water vapor feedback, show the most interkernel variability near the poles. However, the albedo feedback and the shortwave cloud feedback stand out in having far greater standard deviation near the poles compared to the temperature water vapor feedbacks. Another interesting feature I just wanted to point out is in the water vapor feedbacks, and this is possibly because the models that produce the water vapor kernels can have a double ITCZ. Actually, in the standard deviation, you can see a kind of double ITCZ pattern there. We can take a closer look at the latitudinal variations by now looking at the zonal means. And each line here is for one of the 11 kernels included in ClimKern. And again, nearly all feedbacks show the greatest spread near the poles and specifically the Arctic. You can see that that spread much greater than the others when we look at the surface albedo feedback over here on the right, which is just brought down by 4 units to make it on the same scale as everything else. And the shortwave cloud feedbacks. Those are related. You need the surface albedo feedbacks in order to calculate the cloud feedbacks. The shortwave cloud feedbacks, at least in this kind of standard framework. So not super surprising. When we look in global mean, I have the, for each kernel and then the kernel means here on the bottom. Lapse rate, Planck, water vapor, albedo, and our cloud feedbacks. The Planck feedback actually has the greatest standard deviation. But if you think of it compared to the kernel means, it's actually the surface albedo and cloud feedbacks that show the greatest variation relative to their mean values. In fact, the long wave cloud feedback sign totally depends on which kernel that you use, at least in the CSM simulation. I also just want to briefly highlight work that's being written up right now by our undergraduate intern at Princeton, Caitlin Wen. She's been repeating this process using an ensemble of 49 models from CMIP5 and CMIP6 to truly answer that question of how the interkernel spread compares to the intermodel spread. What she's found so far is that, and I think the most straightforward way of interpreting these plots are the red dots show the intermodal spread and the blue dots show the interkernel spread, is that For the most part, the interkernel spread can range anywhere from 10 to 50% of the intermodel spread in terms of global average, except for the Planck feedback, where actually the interkernel spread is larger than that of the intermodel spread. If we switch and instead look at something like the Arctic region, you'll find that typically the interkernel spread is a greater fraction of the intermodal spread than it was in the global average, indicating that it may be more important. Kernel choice may be more important in the Arctic versus the global average. Some takeaways. ClimKern makes calculating radiative feedback so much easier. It standardizes the approach, gives you easy access to 11 different kernels. Kernel choice is likely not negligible, especially near the poles where we see it can at some point even rival intermodal spread. Lastly, I think a good practice that can come from this is if you're doing a climate sensitivity study with these kernels, throw in a kernel sensitivity analysis. Try it at least with a couple different kernels, because that can change the relative importance of feedbacks, especially in something like polar amplification studies. I'll end with, this is an open source project. Definitely need help with it. We started this as a totally unfunded labor of love. There is a quick start guide on the GitHub. There is a paper that was accepted to GMD that further documents this package. And we're also working on a radiative feedback cookbook that showcases ClimKern. For the future, we would love to include cloud kernels, spectral kernels, different ways to calculate the radiative forcing, and feedback's located at the surface. If you have any Python experience and want to get involved, please feel free to go on the GitHub, open up an issue, and we'll see what we can do. That's it. Thank you.
Thanks so much, Tyler. So we already have a question in the chat from Christy. If you want to ask your question, Christy.
Oh, yeah, it's a slightly silly one. It's available through pip. Do you also plan to make it available via CondaForge?
Yeah. That's definitely on the to-do list. It involves just building a like a Conda skeleton, which is relatively straightforward to do. The reason we haven't done it yet is that it requires the ESM-Pi package, which is not available. We were not able to get it to work so far with Conda and that package. But working on it, actually I should open it up as an issue on GitHub.
Okay, thanks. Yeah, I'm just thinking of in terms of integrating with the rest of the Pangeo stack, which I think is what most people are gravitating towards.
Yeah,
okay, thanks.
Totally valid point, and working on it.
And then there's a question from Moritz Gunther, if you want to unmute or.
Yeah, I can ask as well. First of all, thanks a lot for doing all this effort. I think this will save a lot of time for other people. That's really cool. I wondered, there's this other feedback framework where instead of looking at water vapor and temperature feedback separated, they merge this into this relative humidity feedback. And yes. I wonder if you have any plans of including this as well. And yeah.
Yeah, so I think what you're referring to is the method that they use in Shell et al. 2008, and Mark can correct me if I'm wrong, but I believe in his 2020 work he does the same. Yeah, we already have methods for that. That's already included.
Cool.
So yeah, so the only difference is, and to clarify, the temperature functions have a parameter for fixed relative humidity. And if you set that to true, it calculates it as you have asked. There's an additional function where normally they separate it into then like a relative humidity feedback. There's a whole nother function for that. So if it's really easy if someone wants to calculate it that way and group the lapse rate and water vapor together, yeah, that functionality is already there.
Great, thanks.
Thanks.
We have time for maybe one more question. Okay, we have someone raise their hand if you want to unmute.
Yeah, I was just wondering how you calculate cloud feedbacks without cloud radiative kernels. Do you adjust the CRE basically in
Yeah,
order to do that?
yeah, great question. Can everyone see the cloud feedback slide I have up right now still?
Yeah, it looks good.
Yes.
Cool. So I didn't have time in the talk to go over it. Would love to at some point include I think there's advantages as Mark and Brandon will talk about to using cloud radiative kernels. For right now, we have the two say classic ways of calculating cloud feedback. So you can do it either using the residual method, where you sum up all of the non-cloud feedbacks and the radiative forcing, and you say that the cloud feedback is whatever's left over. And you can also do it using the adjustment method, where you use the difference between clear sky and all sky feedbacks to adjust for cloud masking of the change in the cloud radiative effect here on the bottom. So yeah, great question. We have functions for both.
Thank you.
Awesome. So let's move on over to Mark Zelinka. Thanks to Tyler again for a great start. And we'll continue on with our kernel theme.
All right, thanks a lot. Can you see that okay?
Yeah, it looks good.
All right. Yeah, thanks for the opportunity to present here today. Let me just move this out of my way. I'd like to acknowledge my co-authors on this study, Liwei Chow, Tim Myers, Yi Chin, and Steve Klein. So as Lazarus was just alluding to, there's also these cloud radiative kernels. And so the idea here is to present recommendations for how to use these best. In particular, if you are separating cloud feedbacks into high and low contributions, and similarly for rapid cloud adjustments to CO2. So why should we care about this? I don't know if you guys know this, but cloud feedbacks drive uncertainty and climate sensitivity. That's been the case pretty much ever since we started intercomparing models to each other in the late 80s, and it extends all the way up to the most recent intercomparison, CMIP5 and CMIP6. So cloud feedbacks are really important for climate sensitivity. Additionally, rapid cloud adjustments. These are adjustments to cloud properties that happen immediately upon quadrupling or doubling CO2 that then affect the radiative forcing. So the larger the rapid cloud adjustment, the larger the radiative forcing in response to CO2. So this is kind of like the stratospheric adjustment, but now in the troposphere and involving clouds. So larger cloud rapid adjustments, larger radiative forcing. And additionally, the cloud feedback and the rapid adjustments seem to be related in some way. In CMIP5, they are actually anti-correlated, such that models with larger rapid cloud adjustments or larger radiative forcing tended to have more negative cloud feedbacks. And then for reasons that we don't fully understand, in CMIP6, this switched, and now they're positively correlated. And this has implications for the spread of climate sensitivity because in CMIP5, this anti-correlation kind of damped intermodel spread in climate sensitivity because the harder that you force the model, the more radiatively damped it was upon warming and vice versa. And so, again, we don't really understand why that has switched, but it has implications for the spread of ECS and additionally for getting very high ECS models. So it's really important to be able to diagnose in detail cloud feedbacks and rapid cloud adjustments and to partition them among different components to get better insights into what's causing them. As Ty just mentioned, the standard non-cloud radiative kernels that he was just presenting do not have a cloud kernel. And that's primarily, as noted here in the classic Soden paper from 2008, is that the radiative effects of clouds, particularly their vertical overlap, is too nonlinear to accurately compute cloud feedback with. So you can't compute a cloud kernel using the standard cloud diagnostics that are available in models. It's a nonlinear process, and you have to somehow account for overlap. So the workaround that we have used is to rely on the ISCIP simulator, or in the case of observations, ISCIP observations. And the advantage here is that ISCIP is reporting cloud fraction classified by visible optical depth, or albedo, and cloud top pressure, which is related to the emission temperature of the cloud. And so you get diagrams that look sort of like this, cloud fraction as a function of those two parameters. And again, these are the cloud fractions that are visible from space. So these are not, these are literally individually impacting TOA radiation. So because these cloud fractions are individually visible from space, that allows you to construct a cloud radiative kernel in this same space that quantifies the impact of each of these cloud types on TOA radiation. And so that's what we did in 2012, and this follows from very closely from previous work that was done in the Hartman group, both by Dennis and by Terry Kubar. So we construct, using offline radiative transfer model, these kernels. So here's the long wave kernel, short wave kernel, and the sum of the two. So again, this is the sensitivity of TOA long wave radiation to cloud fraction changes in each of these bins. It's positive, indicating that as you increase cloud cover, you decrease the loss of OLR to space. And similarly for the shortwave, increasing cloud cover increases the shortwave reflectivity, so a negative kernel there. And I'm not going to go into too many of the details of this. I think many of you are probably familiar with how these cloud radiative kernels look. And this is just the global average kernel. Of course, these vary spatially and seasonally. So what you can do when you have these kernels is then convolve them with the change in cloud fraction that's in this same space, this cloud top pressure optical depth space. And that gives you the radiative impact of each of these 49 cloud types. And when you sum over that entire product over the whole histogram, you get the total change in cloud-induced radiation anomalies. And if these are normalized by temperature, that's a measure of the cloud feedback. Or if we're looking at rapid cloud adjustments, it would be the rapid cloud adjustment to doubling of CO2. The real advantage of this technique is then it allows you have, again, the radiative impact of 49 different cloud types. And so you can do things like this, where you say how much of the feedback is coming from high, middle, or low clouds. And we typically also will ask how much is coming from changes in the amount holding all the other properties fixed versus the vertical distribution of clouds in the histogram or the optical depth distribution of clouds in the histogram. And so it's really good for getting insights into the processes that are causing the feedback and getting the robust cloud feedbacks, or where the large intermodal spread is, where the large disagreement is. So that's been helpful. One thing that has not really to date been addressed so thoroughly with the cloud radiative kernel technique is the fact that because we're relying on passive satellite simulators, you have obscuration effects. So just to give a schematic of this, this is showing a sample situation in the control climate where we have a high cloud that partially overlaps a low-level cloud. And because graphic design is my passion, these are going to be rectangles. And so in reality, when you're looking at the reflected shortwave from this scene, you basically just see a big white scene. But from the ISCIP or the cloud radiative kernel perspective, you've got a high cloud over part of the scene, and then you've got this small portion of the scene that's occupied by visible low clouds. And underneath the high cloud, the low clouds are completely obscured, so you don't see those. So let's say in the perturbed climate, the high cloud increases, and now it covers up that low cloud, which has not changed in this scenario. In reality, there's really no appreciable change in shortwave reflection. You've just covered up a white surface with a white surface. But in the ISCIP perspective, what's happened is that you've had a big increase in high cloud and basically a large decrease in low cloud. You've hidden that low cloud. It no longer sees it. So in the cloud radiative kernel technique, it's going to say, okay, you've lost low cloud. We'll multiply that by the kernel, and you're going to get a big positive heating from low clouds. And similarly, the high clouds have grown, and the kernel doesn't know anything about what you're covering up. It assumes you're covering up ocean, dark ocean, or whatever's underneath. So you're going to get a big cooling from that increased reflection of the increased high cloud. And obviously, this is not ideal. In reality, what happened was nothing, and what you're attributing things to is a big loss of low cloud, which didn't happen, and a big gain of high cloud, which did happen, but probably didn't have that large of a negative radiative effect. You could do the same thing in reverse and you get similar pathologies that happen here. So how do we deal with this? This has been dealt with before, so this is not new. It's just kind of we're putting recommendations for how to do this in the framework that exists. So you can deal with obscuration effects by basically renormalizing the retrieved low cloud fraction by how much of the scene above it is clear sky. So take your retrieved low cloud fraction that the satellite simulator sees and divide by the fraction above it that is clear sky. So 1 minus the high cloud fraction. And this is our unobscured low cloud fraction. Well, we can write that as the sum of a mean state and a perturbation and expand things out and do some algebra, and we get a new expression for the retrieved low cloud fraction is the change in unobscured low cloud fraction. That's sort of our true low cloud response, plus obscuration effects. This is entirely due to high clouds changing and hiding or revealing low clouds, plus obscuration terms. So we can write that more in kind of more English as our original low cloud anomaly is a true low unobscured component plus obscuration plus this covariance. Okay, so let's try to incorporate this into our framework. And a lot of this is really just counting the beans in a different way, but I'll argue that it makes sense to do this. So we typically expand, as I mentioned, our low cloud of feedback into amount, altitude, optical depth, and a small residual component. So now we can do that with just the unobscured part of the scene. And so we still have these two covariance and changes in obscuration terms hanging around. What we're proposing here in this modified decomposition is for the modified low cloud feedback to now absorb that covariance term into the error term, which is, they're both extremely small. So we're gonna try to conserve the number of components in our decomposition. So let's absorb the covariance into the error and define a new error term. So this is our proposed modified low cloud feedback or adjustment. The high cloud original feedback is similar. We have an amount, an altitude, an optical depth, and an error component. And as you recall, I mentioned earlier that this obscuration term is entirely due to changes in high cloud amount that either cover up or reveal low cloud. So it's really a high cloud amount term. So let's absorb that obscuration term into the high cloud amount feedback and define a new modified high cloud amount feedback. So this is our new high cloud feedback decomposition and low cloud feedback decomposition. This total is the sum. It doesn't change based on this decomposition. You're just kind of counting the beans differently. But in summary, you're taking away the obscuration from the low cloud feedback and you're giving it to the high cloud feedback, particularly into the high cloud amount feedback. So you're just kind of moving these terms around a bit. And I'll argue for why this makes sense with some examples. So here's what the multi-model mean cloud amount feedback looks like. This is from AMIP plus 4K runs. Let's start at the bottom here. So here's the original low cloud amount feedback. And this is what happens when you modify it to account for obscuration. And what you notice is that in some of these regions with large positive feedbacks, they've been reduced somewhat. And here the difference shows you where those regions are. These are areas where high clouds increased, covering up the low clouds and giving you this anomalously large positive low cloud feedback. So we're correcting for the fact that high clouds increased in these regions, covered up the low clouds, and kind of gave you this apparent strong low cloud feedback that is essentially biased high. And what you take away from the low cloud feedback, you give back to the high cloud feedback in equal measure. So everywhere that you had a negative value here was a region where high clouds increased, and the kernel initially thought, oh, you're covering up oceans, so that's a big negative feedback. In reality, all you did was cover up low clouds. So you really did nothing to the radiation. So the modified high cloud feedback is much more muted, as you'd expect when you do these corrections. This also has implications for the intermodal spread. So what you notice is that the intermodal spread in both the high and the low modified feedback is smaller when you do this correction. And so you might be asking, well, how is that possible? The total has to be the same. The total variance has to be the same. But you've reduced the spread in both the high and the low cloud feedback. And the answer is that you've gotten rid of basically an artificial anti-correlation between these two components. So typically models that had a large low cloud feedback were the ones where the high clouds were covering up the low clouds. And so that's entirely an artificial anti-correlation that we were seeing. And when you do this modification to account for obscuration changes, you pretty much wipe out that anti-correlation. So I think of this as very analogous to the kind of held-in-shell relative humidity framework, where when you used to have a large anti-correlation between lapse rate and water vapor feedbacks and the standard decomposition, when you recast things in terms of relative humidity changes, you find that that anti-correlation goes away, and you can really focus in better on the true spread among models. So if you look at individual models now, this is the global mean cloud feedbacks for low clouds at the bottom and high clouds at the top. The black is the original decomposition, and the red is this modification. So for most models, you've got this situation going on where high cloud increases and covers up low clouds. And this tends to make the low cloud feedback too strong. It biases it too positive. You're getting credit for low cloud changes that are really not low cloud changes. It's just high clouds covering them up. So the true low cloud feedback is weaker. The red dots are to the left of the black dots. And then, conserving the total, the high cloud feedback is then a bit stronger as well. You've taken away that from the low clouds and given it to the high clouds. Now, this is the case for most models, but there's some exceptions. For example, HAD-GEM here is a really prominent exception, which actually experiences reduced obscuration. So its true low cloud feedback is actually like nearly twice as large as what you would have diagnosed kind of naively by using the output from the histogram in the raw sense. So it can have big effects in individual models that are pretty dramatic, as noted here for HAD-GEM. As I mentioned, as soon as you quadruple or double CO2, there's rapid changes in clouds even before the planet has a chance to warm, and this affects the radiative forcing. And so in the original decomposition, we had these really large negative low cloud adjustments. And when you do this correction, it turns out that those are significantly reduced. You can see the difference here. And this is because right as you impose the CO2, there's a very large decrease in upper level clouds, and those reveal low clouds. So much of this negative low cloud amount adjustment was artificial. It was just low clouds being revealed by the removal of high clouds upon quadrupling. So it very much changes your partitioning of where the adjustment comes from. The original has it mostly coming from the high clouds with very little contribution from the low. And in reality, it's a very large low, positive low adjustment with a very small high adjustment in the multi-model average, global average. And then, you could look at this for individual models as well. So in all models, it's pretty systematic. Decreased high cloud fraction reveals low clouds, and that gives a negative bias on the low cloud adjustment. And the true adjustment is much more positive, and then the reverse for the high cloud adjustment. So to conclude, the radiative kernel technique is useful for diagnosing cloud feedbacks and rapid adjustments, partitioning into contributions from different cloud types, and breaking down the feedback into contributions from amount, altitude, and optical depth components. We recommend for the 5 people out there that are doing high versus low cloud feedbacks using this method that you account for obscuration effects when you diagnose these things. It improves your mechanistic interpretation of the results. And as I mentioned, with these kind of spurious anti-correlations that exist in the original decomposition, it removes these artificial relationships that aren't physical. It's worth noting that no decomposition that relies on cloud information from passive satellite retrievals can ensure that the radiative effect that you're attributing to a given cloud type is really due to that cloud type. There's many pathologies that creep in when you're using passive retrievals like those from ISCIP. Where a given cloud type at a given location in the histogram may not actually be at that location, or the properties of that cloud type may be affected by clouds at other locations. So what I've been calling true throughout this is really in quotes. It's you're always dealing with this caveat when you're working with ISCIP or any other passive retrieval. The paper is now published and the code is available. That was really the main point, was to provide code for the community to use to do these calculations. And there's a Jupyter notebook to kind of illustrate the different calculations as well. And before I conclude, Jen K wanted me to remind everyone that abstracts are now being accepted to the CFMIT meeting, which will be in July of this year. I believe the abstract deadline is April 4. So thank you very much for your attention. I'll be happy to take any questions.
Awesome. Thanks, Mark. We have time for one question, and then we'll have the rest of the discussion in the chat in order to move on to Brandon. So does anyone have a question for Mark? A question from Shah. Do you want to unmute yourself?
Yeah, I'm just curious, like how much difference this obscuration effect can make over polar regions, especially over an ice-covered domain, because we already see that some effect mostly over the ocean.
I think it's somewhat limited because the effect is primarily in the shortwave. And so if you've got an ice-covered scene, the kernel itself is very small because whether or not there's a cloud there doesn't matter too much, and the kernel will know about that because you map it to the albedo of that scene. And also in the polar, for much of the year in polar night, you're not going to have an effect either because it's in the shortwave. So I would expect this to have a fairly muted impact at high latitudes where there's a lot of ice, primarily because, again, it's a shortwave effect, and presence or absence of clouds is not going to be as big of a deal over ice.
Awesome. We have a question in the chat, Mark, and someone has raised their hand, but in the interest of time, we have to move on to Brandon. So
okay, I'll answer
Maggie, maybe you can put your question in the chat. Yeah.
Thanks.
Can you see my slides?
Looks good.
Perfect. All right. Yeah, thanks to the organizers for inviting me, and thanks to Mark and Tyler for setting things up quite well. So I'll be talking about some work developing a new method for diagnosing effective radiative forcing from aerosol cloud interactions and climate models. And I want to thank my collaborators, specifically Casey Wall and Nick Letzo, and also a few others who helped with the simulations that I'll talk about here today. And I'll just briefly mention that the paper about this work came out just a couple days ago in ACP. So if you're interested in reading a little bit more in detail about this new method, I would encourage you to check it out. So we're going to kind of switch gears a little bit away from cloud feedbacks and into aerosol cloud interactions. So I'll kind of give a little brief overview into what we're going to be talking about. So when it comes to ACI, we typically kind of tend to break things into two different categories. One is the Toomey effect, which is kind of this microphysical process that occurs in clouds where with the introduction of an aerosol perturbation under the assumption of a fixed liquid water content in a cloud, you're going to see an increase in cloud droplet number concentration. And what that results in is a cloud with smaller, more numerous cloud droplets, increasing the surface area of those droplets, enhancing the reflectivity of the cloud, and leading to a cooling effect. So the Toomey effect is kind of separated from what are called cloud adjustments, which occur on kind of slightly longer timescales in response to this microphysical change in the cloud. And so there's kind of a couple different mechanisms that can occur here. On the one hand, with these smaller droplets, you can have enhanced evaporation. So these smaller droplets can evaporate more quickly, shortening either the lifetime of a cloud or just decreasing the water content of the cloud. But on the other hand, due to smaller droplets, you kind of slow the process of collision and coalescence, which can reduce precipitation in a cloud, extending its lifetime or increasing the water content of that cloud. And so we typically separate these adjustments into a cloud fraction adjustment and a liquid water path adjustment. So taking that all together, that's kind of where ERF-ACI comes in. And so ERF-ACI is just the change in top of atmosphere radiative flux from both the Toomey effect and the cloud adjustments. And so I probably don't have to remind anyone of this, but essentially, why would we care about diagnosing ERF-ACI in models? Aerosol indirect effects remain kind of the largest contributor to uncertainty in historical climate forcing. And so in order for us to kind of improve our predictions of how the climate will evolve in the future, we really need to continue to try to hone or reduce the uncertainty in the spread that we currently see. And so I'll kind of just briefly jump right into the methods. As kind of you kind of could have guessed, we rely on a cloud radiative kernel here. And so given that Mark already alluded to this, I'll kind of walk through this section a little faster. But essentially we rely on two different components. So first off, I'll talk about the cloud fraction histogram. And so this is similar to what Mark was mentioning with the ISCIP satellite simulator and ISCIP observations, except that we're relying on the MODIS satellite simulator, but it's essentially the same idea holds. And I want to point out kind of two key differences between what Mark has been talking about and what is typically done in cloud feedbacks and our work here, which is essentially that this joint histogram is actually partitioned by effective radius and liquid water path, which are two key cloud properties relevant to ACI. And then instead of looking at a pre-industrial and 2x CO2 run, we're focused here on control or a pre-industrial aerosols and a present-day aerosols pair of simulations. And so you can note here that this is a change in liquid cloud fraction. So the work that I'll talk about following this is all just focused on the aerosol effects on warm clouds. And then the other piece of this puzzle is the radiative kernel, which I won't spend much time talking about, but I'll kind of note this general pattern that you can see where clouds with smaller droplets and higher liquid water path have a larger radiative effect due to their kind of thicker enhanced reflectivity. I'll briefly mention that there's no reason that you can't extend this method to ice clouds, which is kind of ongoing work, but I won't talk about that here today. So just to kind of take a step back and walk people through how we're diagnosing ARF-ACI, again, we're relying on these two simulations where the only difference is the aerosols that we prescribe. From that, we're able to get this change in cloud fraction, specifically in that joint histogram framework, convolve that with the radiative kernel, as Mark was mentioning earlier, and that gives us not only the estimate of the total ARF-ACI, but we're able to decompose it into those three processes or three terms that I mentioned earlier. And then everything that I show from here on out is from a subset of 5 CMIP6 class models. So I'll just jump right into the main results. So what's being shown here is the ensemble mean results from our 5 models. In panel A, you're seeing the total aerosol forcing on warm clouds, and then panels B through D are the individual terms that are contributing to that total forcing. And so I kind of want to walk through a couple things in this figure to note. To start with, kind of the good things that we're noticing is that the GCMs tend to agree on the kind of major spatial patterns of the Toomey effect and naturally the total aerosol forcing. And we're really seeing strong agreement in areas where we'd expect the spatial signature of the Toomey effect to be really strong. And so these are industrialized regions where historically we've seen enhanced emissions. And so that's kind of popping up in these regions of East Asia, parts of the Eastern US, and also parts of Europe. And so that's where the models are seeing really strong agreement and kind of with results that we would expect. Kind of some of the bad or maybe the downsides that we're seeing, if you look at panel D, that's the cloud fraction adjustment term, and the models don't agree almost anywhere about whether there's a cooling or a warming effect from this adjustment term. And also, you can note that there's no real spatial pattern, unlike what we're seeing with the Toomey effect. And so that's kind of one downside that we see from these results. And then another one that kind of gets glossed over by focusing on the spatial patterns is there's really this large disagreement between models in terms of the magnitude of these forcing terms. And so what I'm plotting here on the top 2 plots it's just the Toomey effect from 2 individual models. And so on the left, you're looking at E3SM, and on the right, you're looking at MIROC-6. And so despite the fact that you can kind of see that these areas, these areas of enhanced emissions over the historical period tend to agree in terms of their pattern of the cooling effect, you're seeing in E3SM actually almost a 4 times stronger cooling from the Toomey effect. And so not only is there an element of spread being introduced in disagreement over some of the warming or cooling effects of the adjustments, you're also just getting some spread in terms of the magnitude of cooling from the Toomey effect. And so that really motivates us to try to understand what might be driving this. And so I'm going to kind of shift gears to thinking about mean state biases in models and really this idea of the MODIS joint histogram as an observable quantity. So I'm going to kind of walk through this figure. It's a little bit all over the place, but essentially what is being plotted here is those same MODIS joint histograms that I've been showing you of cloud fraction, but instead we're looking at a normalized quantity. And so essentially the bins in yellow are the bins that have the highest amount of cloud fraction. And this allows us to really visualize the distribution of clouds in this effective radius liquid water path space. And so the leftmost plot that you're seeing is actually from observation. So this is what the MODIS satellite is actually seeing over a period from 2003 to 2014, specifically looking at the Southeast Pacific stratocumulus region. And so kind of a couple things to note is just there's kind of this maximum in small droplet, lower liquid water path clouds. And then there's kind of some amount of clouds with larger droplets and high liquid water path. And so that's kind of what we would expect to see in the real world. And so we want to evaluate how models are simulating clouds in this region as well. And so what's being plotted in the remaining 5 histograms from moving towards the right is GCM output from a set of nudged historical simulations over that same time period of the observations we're looking at, just to kind of give the best apples to apples comparison here. And there's kind of 3 categories of our models here. We have E3SM, which seems to not only capture kind of roughly the same amount of clouds in this region, but also their distribution in this phase space. CSM2 and NOAA-CESSRST kind of lack a certain amount of clouds and also are skewed a little more towards larger droplet, higher liquid water path clouds. And the 2 MIROC models have completely different distributions and also about half as many clouds in these regions. And this kind of applies broadly with the MIROC models where they suffer from an undetermined phase bias, which I don't really have time to talk about right now, but I'm happy to answer questions about afterwards. And so what this really goes to show us is even within our 5 models, there's a really broad diversity of mean state cloudiness that might be influencing our estimates of ERF-ACI. And so what we present here is our attempt to kind of connect the MODIS joint histogram observations with understanding the spread in the components of ERF-ACI that we're seeing in order to kind of motivate a way that moving forward we can attempt to constrain that large uncertainty that I was showing at the beginning of this talk. And so it's being shown here on the x-axis as we're just looking at the global mean nudged liquid cloud fraction from those historical simulations that I just mentioned. And on the y-axis, you're looking at 2 of the components from our decomposition, the Toomey effect and also the liquid water path adjustment. And what can kind of clearly be seen is even with our 5 models, the strength of these 2 components is really hinging on kind of the base state liquid cloudiness in these models. And so you're seeing kind of towards the left, MIROC, which is hovering around 20% liquid cloud fraction, is really producing near 0, so almost no cooling effect from both the Toomey and liquid water path adjustment. Whereas as you move towards models like E3SM and CSM2, which have sufficiently more liquid clouds in their base state, you're getting increasingly negative or stronger estimates of the Toomey effect and the liquid water path adjustment. And so while in the past you might have seen this spread and just attributed it to model diversity, here we can really try to connect what we're seeing in the spread in those components with perhaps observations. And so this vertical line is just showing the liquid cloud fraction from MODIS observations over that same time period with a shaded standard deviation in time. And perhaps what this indicates is models like E3SM and CSM2, which are well documented to give strong estimates of the cooling from aerosol forcing, resemble their liquid cloud state, resemble kind of what we see in observations and perhaps are providing more accurate estimates of aerosol forcing. For this to really become something like a true emergent constraint, this would need to be tested with obviously a much larger ensemble of models, as well as tested in kind of subsequent generations of CMIP models. But this really begins to point towards a direction where we can maybe attempt to understand the spread that we're seeing in ACI with kind of just mean state biases between different GCMs. So I'll kind of leave these three things up. Hopefully in the last kind of couple of minutes, I've been able to show that substantial spread in ERF ACI and its components can be linked to mean state cloud biases. Within the models analyzed here, the spatial pattern of the Toomey effect, especially its cooling over industrialized regions, shows a lot of agreement, but that kind of hides this element of magnitude that is also contributing to the spread. And then lastly, we introduce a computationally efficient quantification of individual components of ERF ACI. And I'll kind of leave it on that note because I haven't really mentioned, but existing methods kind of fall into two categories where either they're not actually able to disentangle each of these three components of ERF ACI, or the ones that can rely on kind of very frequent specialized output from models. And so we kind of provide a method that fits nicely in between, and hopefully will kind of be able to contribute to the growing work of trying to better understand GCM spread and ERF ACI. With that, thanks for listening, and I'm happy to take questions.
Thanks so much, Brandon. Do we have any questions for Brandon? Feel free to raise your hand or unmute yourself. I have a quick question, Brandon. How much does the fact that you chose 2000 as your kind of reference year change things? Like if you had looked at 1980 or something, since the aerosol patterns have certainly changed.
Yeah, I think there's definitely been work that's been done kind of evaluating the sensitivity of, you know, if you use like 2010 or 2000, or yeah, year 2000 aerosols, and how that impacts your estimates of ERF ACI. As far as I can tell in the literature, that ends up being order like 0.1 watts per meter squared. So it maybe doesn't make a big difference in the global mean. I guess what maybe would change is if we go back to those spatial plots that I was showing, you might see different patterns where kind of, I would guess in the 1980s, you'd see maybe a little bit of a stronger pattern over the US and Europe, where kind of emissions kind of have shown great trends over the last 20 years.
Thank you. Any other question for Brandon before we wrap up?
I have a quick one. So you showed E3SM-V2, right?
Yeah.
So that's the one that's supposed to not have the unrealistically strong aerosol cooling.
That's correct. Yeah, and yet it's still in our testing, it's showing strong forcing for liquid clouds. So there is this whole component that, you know, this is showing estimates of one set of phase of clouds, right? There's a whole story of what's happening with ice clouds that this kind of not glosses over, but we haven't gotten to. So I think that also, you know, you might see different changes in E3SM in terms of what it's estimating for kind of the forcing on ice clouds. But it's a good point, yeah.
It is pointing towards strong. Well, you need more models, but it is pointing towards strong. Yeah, interesting. Thanks so much.
Awesome. So thanks to our three speakers today, to Tyler, Mark, and Brandon. Hope everyone enjoyed Kernel Month. I'm going to stop the recording now, but thank you so much for everyone who came out on this Friday morning or afternoon, depending on where you are. All right, take care.
Thanks, Matt.
Thanks, Matt.
Thanks, everyone.
Thank you.